Welcome back after your drink. I'm glad to be kicking off the solutions section, moving on from problems. My favorite equation is the superposition equation, 1 + 1 = 1.8. Okay, my talk is based on chapter 6, observational models. I got a couple of co-authors. One is here, but my comments are personal. They're certainly not, they don't have to endorse them. So observational models, principally, we're looking at investigation, and when we look at intrusive investigation, we've divided that into 3 sections: the geotechnical investigation, where we're really looking at strata profile, collecting some basic parameters. That would be followed perhaps by a groundwater investigation, so a period of monitoring, sample testing, establishing the groundwater levels and the groundwater quality. And then I'm specifically talking about the hydrogeological investigation, principally pumping tests, and pumping tests that are applied to the design of groundwater control systems. And I'm really going to try and just address 2 questions. Why are pumping tests useful? And I'm going to talk briefly about permeability, well yields, boundary conditions, and how do we get the most out of them. And I'm going to look at low permeability soils, Martin talked about yesterday, partial cutoffs and KV, recharge, and pump test phases. So we have some standards for pumping tests, and they focus on methodology, monitoring methods, frequency of readings, test sequences, test procedures. They give advice on flow rates, some advice on piezometer locations, not much information on well design or specification. And they're typically sort of single wells, and I think that these specifications are really designed for assessing water resources more than designing dewatering systems. So the objectives for a pumping test from a dewatering perspective fall into 3 main areas: permeability and permeability profile. But big reveal from Martin yesterday, it doesn't measure the permeability, we get a measurement of the transmissivity. So we specifically get a measurement of the horizontal permeability times the depth. And if we don't know the depth, we might not know that much about the permeability. We can also get the storage coefficient out of it. Boundary conditions are certainly key, and as long as we pump hard enough for long enough, we should get some good information on boundary conditions. And well yield, which is another point that Martin made, an important element in the design of a system. So from a dewatering perspective, the permeability is one thing, but we have these other things that we're trying to find out. A bit of an admission here, I don't pay much attention to storage coefficient. So sigh of relief from the geotechnical engineers who've never really understood it, howls of horror from the hydrogeologists who are vested in it. But the reality is that almost all the dewatering systems that we do, we can dewater it quicker than it can be excavated. There's always an exception. This is an exception. Big excavation in Dubai in sand. Actually, we could dewater it quicker than they dug it. It was all to do with the way in which the site was released, which caused a problem with timing, and the excavation program was in fact controlled by the storage coefficient. So there's always exceptions to almost everything I'm going to be saying. So methods of measuring permeability, Martin ran through several of these. We've got the field test, non-quantitative, the laboratory tests, and then the quantitative field tests. And I've given them a Toby Roberts gold star rating. And you can see that most of them only merit 1 star. I mean, particle size distribution, I did go for 2 stars. I angst for quite a long time about whether Packer tests should also have 2 stars, but in the end, I've just seen too many that don't give useful results to go that far. The issue with a lot of these tests is partly to do with how they're run, but also a lot to do with scale. All of these, most of these site tests essentially are testing quite a small volume of the ground. And if you're designing a dewatering system, we need to know what the bulk permeability is. So as far as I'm concerned, if I'm designing a dewatering system, I want to know reasonably accurately what the flow is going to be and how many wells I need. Pumping test is pretty much the only game in town. And you can have single well test or a group test, which I'm going to talk about. Oh, that was a good change, wasn't it? So just back to boundary conditions. Boundary conditions are vitally important with this kind of situation. We've got a cofferdam in the river. The cofferdam doesn't just tows into river gravels and chalk. You're clearly going to get a lot of flow coming in. It's a 10 metre below high tide for a barrage foundation. And there was a lot of question, was this feasible? Could this be done in the dry? But the flow is going to be excessive and critically dependent on whether the river is a fixed head boundary condition directly connected to the gravels or not. The site's in the middle of the river, so difficult to do a pump test. We were able to do the test. We did the test on the shore, and from the data that we obtained from that, we could work out that the riverbed was had a layer of clay and, or a layer of silt, and effectively was isolating the river, and it was feasible to do it, albeit relatively high flows. The other boundary condition we've just mentioned is well yield. So the groundwater has to flow from the ground through our filter pack into our well screen, and what we find, and Martin mentioned this, is that the well yield in high permeability soils essentially is controlled by the well size and the pump size by and large. It's fairly easy to design efficient wells in high permeability soils. But in low permeability soils, the well yield is very much controlled by the formation. And what it means when we're looking at the pump test is that the test well spec is a good idea if that is the same as the planned well specification. And that turns out to be a really great conclusion, because if we're trying to design a pumping test, there's a load of things that we have to choose, and if we decide that we're just going to use the same kind of well that we're going to use for our subsequent dewatering system, it knocks off most of them. We've still got to work out where we're going to put the water, piezometer locations, response zones, and on the piezometers, and think about the test phases. But it's a really good start. So a single well pumping test is a perfectly good test and the most commonly carried out. And it's certainly appropriate where you're planning to use, in this case a partially penetrating well, to dewater an open cut excavation. It doesn't matter if the ground is slightly anisotropic, certainly a factor of 10, no problem. Factor of 100, could be an issue, probably okay actually, but any more than that, not okay. So the well specification, as I said, as the main works. I've proposed some piezometer locations here. You want something close to the well, other stuff across the width of the excavation, something if you've got a structure you're worried about, and perhaps some far field stuff. And with that array, you'll get a good idea of what's going on and get the information that you need to design the test. And you can put in a deeper piezometer if you want, and that might be useful if you wanted to know what the vertical permeability is, because it would give you some information about that, and if you were concerned about uplift, that might be a sensible thing to do. So here's the kind of scheme it is. This is a big open cut excavation in a sandy aquifer. It was relatively anisotropic, in fact, probably greater than 10, but single well pumping test, perfectly effective. Also, if you've got a pressure relief system, you've got this kind of situation. Here, you've solely got horizontal flow. You're not concerned with the vertical permeability of that aquifer. And a sort of standard single well pumping test in a medium permeability aquifer will tell you all that you need to know to design that kind of system. Oh, I've got another one there. But what about if we're trying to do some work in the Lambeth Group channel sands? This is the face of a tunnel in central London, one of the Crossrail tunnels. You've got clay at the top, clay at the bottom, and then you've got some pretty low permeability silty sand in the middle there. And that is being dewatered. But if you wanted to investigate that, how useful would a single well be installed into that? You wouldn't get a lot of water out of one well. You might get a bit of information about the permeability, about the well yield, but it's going to be quite low. I certainly would argue you may not get much useful information from one well, just because you wouldn't put enough stress on the aquifer. So this is the diagram that Martin put up yesterday of the various range of applications of dewatering systems. And I'm really saying, and I think Martin was also saying, what kind of test should we be doing if the permeability is less than, I've gone slightly higher than 10 to the minus 5, covering the range where you've probably got to apply vacuum to get much to happen. And I think you need to be seriously thinking at these kind of permeabilities about a multi-well test, putting in 2, 3, or even 4 test wells, probably to the same specification, probably quite close together, 5 to 8 meters in a grid, in a triangle, with a piezometer in the middle, and then some piezometers going away. So this kind of test is appropriate in low permeability aquifers. And what we're trying to do is really just maximize the stress that we put the aquifer under so we get something we can measure. Adding a vacuum, as Martin said, we really want to know what that does. We can investigate the well spacing because we can turn on the wells sequentially in the course of the test. That gives us some useful information. And similarly, if you're looking at a well point system or something, you might just want to put in a section of the well point system, 10 or 15 well points. That kind of test is actually much more useful than a single well test. So moving back to permeability, I mean, it's most obvious in rock, but permeability is, of course, a scale-dependent feature. And where you chose to measure the permeability with your packer tests or whatever in this would give you very different results. So, I mean, a pumping test can still be useful in this because it should, if you've got piezometers, it should reflect what's happening in the ground. Although you may get quite confused with very high yield or relatively low yield. So pumping test gives the average horizontal permeability, but no information about the variation of permeability with depth. Here, we were usefully able to combine the pumping test data with some packer test data, and in the softer chalk, where you couldn't do packer tests, we had variable head tests in piezometers, and that's been plotted up here against depth, against permeability, with the ground profile there, so we're in the chalk. And you can see a couple of orders of magnitude reduction in permeability in the chalk with depth. If you've got an open cut excavation, that's perhaps not interesting, but if you're trying to decide how deep to install a cutoff to reduce the flow, that is extremely interesting. And another way you can investigate that is through geophysics, specifically fluid logs. I think this is actually the same one that Ian showed earlier from Deptford Church Street. So it's an uncased borehole in chalk, but any fissured rock you can do this in. And it's got a caliper log, and that, I think I've got an extra, there we go. Shows a fissure just below 74. You can see there's something happening with the temperature and the conductivity of the water. But the uphole velocity, we put a pump in the well, pump it, and at the same time we measure the uphole velocity in the well, and we can see in this case, remarkably, that all of the water that we're pumping is entering the well through one fissure at about 74, 75 meters below ground level. They're not often as clear-cut as this, I have to say, but they can be very useful. Of course, you can't always do that kind of test, certainly if you're not in rock. So another way of doing a test would be to do a multi-well test, but at different depths. So here we've got gravel, sand, silty sand. It's fining downwards, always a worry for a dewatering contractor. And we've put a well into each of the layers. We need quite a lot of piezometers to understand what's going on here. So this allows us to investigate the variation in permeability with depth. We can look at the connectivity between the layers. You need to test the wells individually. When you try and analyze these kind of problems, one of the things you find is that there may not be a unique solution. So unless you can actually nail down one of the permeabilities, it's hard to nail down the rest. And you can also, if the wells are close together, you can pump on them all together and simulate essentially a single well test. So if you're trying to investigate this kind of problem, this is one of the cable tunnel shafts for the London 2012 Olympics. So the shaft is being sunk as an underpin caisson. So there's no cut-off below the depth you can see. They've just excavated, just exposing the chalk, and there's the residue of the thanate sand you can see around the perimeter. The chalk is dewatered with deep wells, but the water in the thanate sand hung up, and there's a couple of stages of well points that had to be rushed in at the last minute. So if you want to investigate this kind of interaction between two aquifers that are linked together. You can really only do this with some kind of multi-well test with wells and piezometers at different levels. This apparently similar picture is very different. Also deep shaft in chalk, but in this case we have a diaphragm wall installed in advance that extends to about 10 meters below the base of the shaft. And what we're concerned about here is how much water is going to come into the base of the shaft. And we need to know that because we need to know where to get rid of it. And if we're worried about external drawdowns and settlement risks, we also need to know it. And here you might look at something like a pumping trial. You test within the cutoff area and you test before and after the cutoff. So it's an observational approach. As I said, it's essential where you've got a sort of partial cutoff and you've got constraints on discharge capacity or a sensitive neighbour. The pre-pump test flow log is the most useful thing. You could actually restrict the screen length of the well and possibly try and look at the permeability around the toe of the diaphragm wall rather than have a long well. You might do that if you weren't in rock. And you'd need a contingency option in chalks, typically a grout curtain or a grout base plug if flows look like they're unacceptable when you do the post diaphragm wall test before they do. And if you're going to do recharge, and because of the licensing arrangements, we're all doing a lot more recharge than we used to. There's really it gets quite complicated. You need to know what the performance of your abstraction well is, the performance of your recharge well is. You've perhaps got a cutoff to help this all work. So you've also got vertical permeabilities and horizontal permeabilities to unpick if you want to design this kind of system. And certainly doing an abstraction recharge trial is a good start. You haven't got the cutoff in place that you're going to be relying on later, but you can perhaps have some separation between the wells. One of the things with all these tests is if you can locate the well where it's actually useful for the main works, then the marginal cost of the test could be relatively low. And certainly that applies to most of the piezometers. So I think you should always be doing an abstraction recharge test where recharge is planned. And again, you need actually to do 3 tests. You need to test each well, probably pumping on it individually, and then do the abstraction recharge. So there's a choice to be made on pump test phases. These were all the phases that I can think of that people talk about. I've highlighted in blue the ones I think that we pretty much always need to do. So we need to check our equipment works. We need to check our piezometers work. And falling rising head test is a good place to start. Yield tests are just really short-term tests. See how much we can get out of the well. Sometimes worth doing. Step tests, I mean, they're really designed to tell us about the efficiency of the well. I'm confident that I've installed the most efficient well. I don't need to know what the efficiency is. Having said that, yes, I like step tests. They don't take long. I think they are generally worth doing, but I don't think they're essential. Background monitoring, absolutely essential. And you certainly need a few days to make sure you understand what trends, and preferably longer. But it's the constant rate test that is of most interest. Stephen pointed out that actually we never do a constant rate test. We always do pump as hard as you can. Get the water as low down as you can in the well, because that's what we're going to be doing. And I don't see, I'm interested in getting to steady state as quickly as possible, because that's the data that I really need to design a system. That's what tells me about boundary conditions. So my focus is on that. I mean, test periods, 1 to 28 days. I think in reality, 3 to 5 days usually tells you pretty much everything you need to know. So that's my recommendation. And recovery, always worth monitoring recovery. Dewatering systems run 7 days a week, 24 hours a day. Good idea to know what happens if it accidentally goes off. And the geophysical testing, that's just horses for courses. Definitely worth doing when you've got an unlined borehole in rock. Other situations may not be good, may not be useful. So how do we analyze these non-standard pump tests? How do we interpret the results? The only real way of doing it is modeling it. So we get our conceptual model, we model the pump test, and we use the data from the pump test to calibrate the model. And if we've designed our model, our pump test correctly, that should tell us most of the key parameters that we need to know. And then we can use the same calibrated model as the basis for the design for the system. So just to summarize, Toby's recommendations for pump tests. Test well spec should usually reflect the planned well spec. I say usually because there are, of course, exceptions. And when you're doing tests at different depths, there are probably going to be some wells there that you're not going to be using for the main works. Think carefully about whether a multi-well test might be worth doing in low permeability soils, and applying a vacuum can be very worthwhile. Geophysical logging, certainly good in rock, flow logs, CCTV, acoustic images. Natural gamma, I mentioned. We don't do a lot of it in the UK, but our operation in Canada does it on every well we drill. And it's an incredibly effective way of picking up clay bands in sand that you didn't realize were there. And that is perhaps something we could be doing more of where we think that risk exists. So multi-well test at a range of depths. If the vertical permeability is a factor in our design, which it's going to be if we've got we're relying on some kind of partial cutoff. Abstraction recharge test, if we're thinking about recharge. Think about what phases to do, but really pay attention to the constant drawdown test, I guess it is. And pump as hard as you can. Aim to reach steady state. That's going to make your life a lot easier on the design. Thank you.